We'll start in about a minute. Today we'll cover section 7.4. The title of that section in the textbook is the Other Trigonometric Functions, and then section 8.1 on graphs of sine and cosine functions. Okay, we'll start with this exercise. Find the exact values for secant, cosecant, tangent, and cotangent of pi over 6, pi over 4, and pi over 3. So secant of pi over 6, remember that secant of pi over 6 is the reciprocal of cosine. So secant of pi over 6 is cosine of pi over 6. And cosine of pi over 6 is the square root of 3 over 2. So 1 over the square root of 3 over 2, the reciprocal of that is 2 over square root of 3. That's secant of pi over 6. Cosecant of pi over 6. Cosecant is the reciprocal of sine. So cosecant of pi over 6 is the same as sine of pi over 6. But sine of pi over 6 is 1/2, and 1 divided by 1/2 is 2. So cosecant of pi over 6 is equal to 2. Tangent of pi over 6. Well, we know now that tangent is equal to sine over cosine. So sine of pi over 6 divided by cosine of pi over 6, or 1/2 divided by the square root of 3 over 2. And when you simplify this, you get 1 over the square root of 3. Cotangent of pi over 6, that's the reciprocal of tangent. So cotangent of pi over 6 is 1 over tangent of pi over 6. Or 1 over 1 divided by the square root of 3. When you simplify that, you just get the square root of 3. We could have done that directly, since the tangent of pi over 6 is 1 over the square root of 3, and cotangent of pi over 6 is the reciprocal of tangent of pi over 6. We could just write down the reciprocal square root of 3. Secant of pi over 4. This is the reciprocal of cosine of pi over 4. So 1 over the cosine of pi over 4 is 1 over, and then the cosine of pi over 4 is 1 over the square root of 2. And 1 divided by 1 over the square root of 2 is just the square root of 2. Cosecant of pi over 4 is the reciprocal of sine of pi over 4. So 1 over sine of pi over 4 is 1 over 1 divided by the square root of 2, and that's just the square root of 2. The tangent of pi over 4, now that's sine of pi over 4 divided by cosine of pi over 4. or the 1 over the square root of 2 divided by 1 over the square root of 2, which is just 1. So the tangent of pi over 4 is 1. Cotangent of pi over 4 is the reciprocal of tangent of pi over 4. The reciprocal of 1 is 1, so cotangent of pi over 4 is also equal to 1. Okay, secant of pi over 3. Well, that's the same as 1 over cosine of pi over 3. Cosine of pi over 3 is 1/2, and 1 divided by 1/2 is equal to 2. The cosecant of pi over 3, that's 1 over sine of pi over 3. Sine of pi over 3 is the square root of 3 over 2. And so 1 divided by the square root of 3 over 2 is 2 divided by the square root of 3. Okay, the tangent of pi over 3, well, that's sine of pi over 3 divided by cosine of pi over 3. Sine of pi over 3 is the square root of 3 over 2. And cosine of pi over 3 is 1/2. The square root of 3 over 2 divided by 1/2 is just the square root of 3. And then the cotangent of pi over 3 is the reciprocal of tangent of pi over 3. So we can write that cotangent of pi over 3 is 1 over the square root of 3. Okay, make sure you know all of the all of the 6 functions evaluated at the special angles. Okay, let t be equal to 11 pi over 6. Use the reference angle to evaluate all 6 trig functions. So let's graph this. 11 pi over 6, well, that's counterclockwise, and it's not quite one complete revolution. It's all but pi over 6. So 11 pi over 6, and the reference angle is pi over 6. The terminal side is in the 4th quadrant, and so cosine is positive, sine is negative, and then we can determine the signs of the other 4 functions just by knowing what the sign of sine and cosine are. So we'll start with cosine of 11 pi over 6. That's equal to cosine of pi over 6, which is the square root of 3 over 2. Sine of 11 pi over 6, well, in the 4th quadrant, sine is negative, so sine of 11 pi over 6 is the negative of sine of pi over 6, or negative 1/2. Okay, and now we have enough information just by using sine and cosine of 11 pi over 6, we can determine what the other 4 trig functions are. So let's just do tangent of 11 pi over 6. That's the tangent of 11 pi over 6 is sine of 11 pi over 6 divided by cosine of 11 pi over 6. So we'll just write down negative 1/2 divided by the square root of 3 over 2. And we'll simplify that a little bit, and we get negative 1 over the square root of 3. Cotangent of 11 pi over 6 is the reciprocal of negative 1 over the square root of 3. So we'll just use that fact. Cotangent of 11 pi over 6 is negative square root of 3. That's the reciprocal of negative 1 over the square root of 3. And then secant of 11 pi over 6 is the reciprocal of cosine of 11 pi over 6. So the secant of 11 pi over 6 is 2 over the square root of 3. And cosecant of 11 pi over 6 is the reciprocal of sine of 11 pi over 6. And the reciprocal of negative 1 over 2, negative 1/2, is just negative 2. Okay, another example doing the same thing. This time, let t be equal to negative 3 pi over 4. Okay, so it's a negative angle. That means we move clockwise. So negative 3 pi over 4, that's going to end up in the third quadrant. So this is negative 3 pi over 4. And the reference angle is pi over 4, equivalent to 45 degrees. So in this third quadrant, sine is negative and cosine is negative. Okay, so we'll start with cosine of negative 3 pi over 4. That's equal to the negative of cosine of pi over 4, which is the negative of 1 over the square root of 2. I'll write it as the square root of 2 over 2, negative square root of 2 over 2. This is what you get if you rationalize the denominator. Sine of negative 3 pi over 4. Well, sine is also negative in the third quadrant, so this is the negative of sine of pi over 4, which is negative square root of 2 over 2. Tangent of negative 3 pi over 4. Well, the tangent in the third quadrant is positive because the tangent is sine divided by cosine, but a negative divided by a negative is a positive. And so the tangent, that's just equal to, tangent of negative 3 pi over 4 is equal to the tangent of pi over 4. And we saw earlier that that's equal to positive 1. Okay, 3 more. Cotangent of negative 3 pi over 4. That's the reciprocal of tangent of negative 3 pi over 4. The reciprocal of 1 is 1. And then secant of negative 3 pi over 4. That's the reciprocal of cosine of negative 3 pi over 4. So the reciprocal of negative square root of 2 over 2 is 2 over the square root of 2, but it's just negative. That simplifies to negative square root of 2. And then cosecant of negative 3 pi over 4. That's the reciprocal of sine of negative 3 pi over 4. So the reciprocal of negative square root of 2 over 2 also simplifies to negative square root of 2. Okay, these are good exercises to do. Make sure that you're familiar with all of those special angles. Okay, the next page, using even and odd trig functions. So from college algebra, you learned what even and odd functions are. Recall that a function f of x is an even function if f of negative x equals f of x, and a function g of x is an odd function if g of negative x equals the negative of g of x. So we'll show that sine is an odd function and cosine is an even function. So let's just let t be an angle that's between 0 and pi. I'll just say let 0 be less than t, which is less than pi. Then that means negative pi is less than negative t, which is less than 0. So first we'll start with sine of negative t. Okay, so if negative t is between negative pi and 0, so that's the third and fourth quadrants. So I'll just sketch in one possible place that we could get negative t. And so the reference angle is t. And in the third and fourth quadrant, so this is just one place that I could have placed negative t in the third and fourth quadrants. So in the third and fourth quadrants, sine is negative. So sine of negative t is equal to the negative of sine of t. So this shows that this is not a rigorous proof, but this is convincing enough that the sine function is an odd function. It satisfies this form, g of negative x equals the negative of g of x. Okay, so sine is an odd function. Useful to remember. Okay, well, similarly, if we construct negative t again, so negative t is this angle, and so the reference angle is t, and in the fourth quadrant, cosine is positive, so the cosine of negative t is equal to the cosine of t. So this demonstrates that cosine is an even function. It satisfies this part of the definition. If f of negative x equals f of x, then f is an even function, and that's the kind of function that cosine is. Cosine of negative t equals cosine of t. So cosine is an even function. Okay, well, now that we know that sine is an odd function and cosine is an even function, we can determine what the other four trig functions are, even, odd, or neither. So let's start with cosecant. So cosecant of negative t Well, that's equal to 1 over sine of negative t, because cosecant and sine are reciprocals. And we know that sine of negative t equals negative sine of t. So this is 1 over the negative of sine of t, which is the negative of cosecant of t. So this shows that cosecant is an odd function. And that certainly makes sense, because since cosecant and sine are reciprocals, since sine is an odd function, cosecant is also an odd function. So I'll spell that out. Cosecant is an odd function. So you can probably guess what's going to happen next. Secant of negative t. Well, secant is the reciprocal of cosine, so secant of negative t is 1 over cosine of negative t. But cosine is an even function, so cosine of negative t is cosine of t. And 1 over cosine of t is secant of t. So this shows that secant is an even function, because secant of negative t equals secant of t. So I'll write that down. Secant is an even function. Okay, well, tangent of negative t. We'll use the fact that tangent of negative t equals sine of negative t divided by cosine of negative t. In the numerator, sine of negative t is negative sine of t. And in the denominator, cosine of negative t is cosine of t. And the negative sine of t over cosine of t is negative tangent of t. So since tangent of negative t equals the negative of tangent of t, that means tangent is an odd function. So tangent is an odd function. Well, since I ran out of space, that's okay in this case, because cotangent is the reciprocal of tangent. So cotangent will also be an odd function. The argument would look similar to this one for tangent. So I'll just go ahead and write that cotangent is an odd function. Okay, so one thing you can remember is that out of all of the 6 trigonometric functions, only 2 of them are even. So cosine is even, and its reciprocal, secant, is even. The other 4 are odd functions. Okay, we'll now write down some things we already know. Tangent of t is sine of t over cosine of t. Secant of t is 1 over cosine of t. Cosecant of t is 1 over sine of t. And cotangent of t is 1 over the tangent of t, but we can also write cotangent of t is equal to the cosine of t over sine of t. Since cotangent of t is the reciprocal of tangent of t, we just write down the reciprocal of sine of t over cosine of t. Hey, a couple of more exercises. Evaluate cosecant of 4 pi over 3. Well, remember that cosecant is the reciprocal of sine, so this is the same as 1 over sine of 4 pi over 3. So we can find sine of 4 pi over 3, and then its reciprocal is cosecant of 4 pi over 3. Okay, so let's go ahead and go through the process of finding where the terminal side of 4 pi over 3 is. So 4 pi over 3 is positive, so we move counterclockwise. 4 pi over 3 is bigger than pi by pi over 3. So we rotate counterclockwise. So that's the 4 pi over 3. And the reference angle is pi over 3. And it's in the third quadrant. So sine of 4 pi over 3 is going to be negative. So it's the negative of sine of pi over 3, which is negative square root of 3 over 2. Okay, so cosecant of 4 pi over 3 is just the reciprocal of negative square root of 3 over 2. So I'll just write that up here. It's equal to the negative of 2 over the square root of 3. So as I've mentioned a few times, you can leave the answer in this form, but if you want to rationalize the denominator, you can if you want. Okay, the next exercise, simplify the cotangent of t times the sine of t. Cotangent of t is cosine of t over sine of t, and then sine of t in the numerator, we can write it as sine of t over 1. And we get a cancellation. Sine of t divided by sine of t is equal to 1. And so this simplifies to cosine of t. All right, the next page, Pythagorean Identities, plural. Okay, so that means not only is cosine of theta squared plus sine of theta squared equals 1. Here I'm using theta. I could use any variable I want. Here I'll just use theta. So we already know this Pythagorean identity, but there are 2 more. One of the other ones is found if we divide every term on both sides by cosine of theta squared. So divide every term by cosine of theta squared. And 1 divided by cosine of theta squared. And then we simplify. Cosine of theta squared divided by cosine of theta squared is 1. Sine of theta squared divided by cosine of theta squared is tangent of theta squared. And 1 over cosine of theta squared is secant of theta squared. So as with a lot of things we've covered already this week, these Pythagorean identities will be used quite a bit in calculus if you're going to end up in calculus. But the nice thing about the Pythagorean identities, if you know this one, everybody should know this Pythagorean identity. You can always derive the other two. So we derive this one by dividing every term on both sides by cosine of theta squared. Then the third one is what we get when we divide every term on both sides of this equation by sine of theta squared. So divide cosine of theta squared by sine of theta squared. Divide sine of theta squared by sine of theta squared. And divide 1 by sine of theta squared. Cosine of theta squared divided by sine of theta squared is cotangent of theta squared. Sine of theta squared divided by sine of theta squared is 1. And on the right hand side, 1 divided by sine of theta squared is cosecant of theta squared. Okay, so those are the 3 Pythagorean identities. Make sure that you know how to find them. So as I said, memorize this one, cosine of theta squared plus sine of theta squared equals 1. And then you can derive the other two whenever you have to. Okay, in this next exercise, cosecant of t is equal to negative 15 over 7. And it's also given that t is between pi over 2 and 3 pi over 2. Well, since cosecant of t is negative, that even narrows down where t has to be. T has to be between pi and 3 pi over 2. T has to be in the third quadrant. So why do I know that? Well, cosecant of t is the reciprocal of sine of t. So sine of t is the reciprocal of negative 15 over 7. So negative 7/15. And we do know that in the second quadrant, that's from pi over 2 to pi, we know that sine is positive in the second quadrant. So t has to be in the third quadrant. Okay, so how are we going to find the other 4? We have 2 of the trig values. Now we need to find the other 4. Well, we can use a Pythagorean identity. If we want to work with cosecant of t equals negative 15 over 7, then we can use this Pythagorean identity and replace cosecant of t with negative 15 over 7, and then do the arithmetic. Or since we also know what sine of t is, we can use this Pythagorean identity. Whichever you prefer, I'll go ahead and use this first Pythagorean identity. I'm going to switch the variable from theta to t, so we have cosine of t squared plus sine of t squared, but sine of t is negative 7/15. So negative 7/15 squared equals 1. And then we just do the arithmetic. Cosine of t squared is equal to 1 minus, and then when we square negative 7/15, we get minus 49/225. And 1 minus 49/225 is 176/225. So cosine of t, if we were just solving this equation independently of the setting, we would say that cosine of t is equal to positive and negative square root of 176/225, which is positive and negative. The square root of 176, so let's see, 176 is 16 times 11, and the square root of 16 is 4. So in the numerator, we have 4 times the square root of 11, and the square root of 225 is 15. Okay, but for our purposes, t is in the third quadrant, and cosine is negative in the third quadrant. So we'll pick the negative solution. Cosine of t is negative 4 times the square root of 11/15. Okay, so now we know what the reciprocal of cosine is for this one. Secant of t is the reciprocal of negative 4 times the square root of 11/15. So secant of t is negative 15/4 times the square root of 11. And we just have a couple of more. Tangent of t. Well, tangent of t is sine of t divided by cosine of t. So we're going to get a negative divided by a negative. It's positive. Since the denominators are the same for sine of t and cosine of t, when we divide, we're going to get a cancellation. And we'll just end up with positive 7/4 times the square root of 11 for tangent of t. And then cotangent of t is the reciprocal of tangent. So we can just write cotangent of t is 4 times the square root of 11/7. So we got all 6 of them. We were given cosecant of t, so we found sine of t, cosine of t, tangent of t, cotangent of t, and secant of t. Okay, the period of a function, the period capital P of a repeating function f is the number representing the interval such that f of x plus p equals f of x for any value of x. So it turns out that the period of sine, cosine, secant, and cosecant is 2 pi radians, or 360 degrees. And the period of tangent and cotangent is pi, or 180 degrees. So it was indirectly made known to us that the period of sine, cosine, secant, and cosecant is 2 pi when we evaluated those functions using reference angles. Okay, we'll do another short exercise on evaluating a trigonometric function at an angle given in radians in the event that your calculator only has the degree mode. So suppose a calculator only evaluates trig functions for angles measured in degrees. Explain how to evaluate sine of 2 pi over 5. Okay, so as you know, convert 2 pi over 5 to degrees. So that means we're going to multiply 2 pi over 5 by 180 degrees over pi. So pi divided by pi cancels. And then we can write 2 times 180 degrees is 360 degrees divided by 5. And 360 degrees divided by 5 is 72 degrees. So you can then just use sine of 72 degrees. That's the same value as sine of 2 pi over 5. Okay, now we'll go ahead and start section 8.1. In section 8.1, we're going to discuss how to graph sine and cosine functions. We'll start out with some tedious work. So here it says, fill in the sine of x values for the given x values. Hey, we've done just about all. Well, we've done all of these multiple times already, so we can go pretty quickly. Sine of 0 is 0. Sine of pi over 6 is 1/2. Sine of pi over 4 is the square root of 2 over 2, or 1 over the square root of 2. Sine of pi over 3 is the square root of 3 over 2. Sine of pi over 2 is 1. Sine of 2 pi over 3 is also the square root of 3 over 2. Sine of 3 pi over 4 is the square root of 2 over 2. Sine of 5 pi over 6 is 1/2. Sine of pi is 0. So far, the x values are from the first and second quadrants, and we know that the sine function is positive in the first and second quadrants. The remaining x values will be in the third and fourth quadrants, so the sine values will be negative. Sine of 7 pi over 6 is negative 1/2. Sine of 5 pi over 4 is negative square root of 2 over 2. Sine of 4 pi over 3 is negative square root of 3 over 2. Sine of 3 pi over 2 is negative 1. Sine of 5 pi over 3 is negative square root of 3 over 2. Sine of 7 pi over 4 is negative square root of 2 over 2. Sine of 11 pi over 6 is negative 1/2. And then sine of 2 pi is 0. A few minutes ago, it was mentioned that the period for sine of x is 2 pi. So when x is 0, sine of 0 is 0. And then one complete period involving both positive output values and negative output values and getting back to 0 is 2 pi radians. Okay, so we'll graph y equals sine of x in the xy plane by plotting the ordered pairs above. So the unit circle just involves finding angles in a circular fashion, and now we're going to stretch out those values on the x-axis. Okay, I'll mention one of the strategies for graphing sine and cosine functions. If we know what the period of the function is, then we can divide the period into 4 equal intervals. So when x is 0, sine of 0 is 0. So the x value is 0. So to the right, I'm going to subdivide the interval from 0 to 2 pi into 4 equal intervals. So 2 pi divided by 4 is pi over 2. So we're starting at 0. And then 2 pi divided by 2, this is the second interval, was pi. And so you can see that each of these subintervals is of length pi over 2. So this number here should be pi over 2 plus pi, which is 3 pi over 2. And then 3 pi over 2 plus pi over 2 is 2 pi. So one period of this y equals sine of x function will occur on the interval from 0 to 2 pi. So we already know that the range of y equals sine of x is from -1 to 1. So now we'll just plot the points. One ordered pair is 0, 0. Let's jump down to what happens when the x value is pi over 2. When x is pi over 2, sine of pi over 2 is 1. So we get this point on the graph, pi over 2, 1. And then at pi, sine of pi is 0. So we have this value, or this point on the graph. And then 3 pi over 2, sine of 3 pi over 2 is -1. So we have this point on the graph. The range value is -1. And then sine of 2 pi is 0. So we have this point. I'll just point out what goes on in between those. Pi over 6 is a 30-degree angle, so it's about right here. Then pi over 3. And then 2 pi over 3, roughly, and 5 pi over 6, then 7 pi over 6, 4 pi over 3, 5 pi over 3, and 11 pi over 6. I skipped over the pi over 4, 3 pi over 4, 5 pi over 4. Those are just the midpoints of those intervals. 7 pi over 4. Okay, but if you plot those other points, we'll just get points that look something like this. Okay, then we just connect the dots. So this is the graph of one period of y equals sine of x. Okay, with a little bit of practice, if you take my advice on dividing the period into 4 equal parts, then you can just plot the points at those points on the interval, and then just draw the sine curve through those points. Okay, so this is one period of we can, if I had room, I could draw another period to the right, or at least a part of one. So if I label this 5 pi over 2, the graph continues in this direction. If I go back to negative pi over 2, the graph continues to the left also. Okay, so we'll fill in this information down here. The period of y equals sine of x is 2 pi. In this one, there is no phase shift, so I'll just say none for phase shift. The amplitude is 1. I'll explain a little bit more about the amplitude in a second. The midline is y equals 0. You'll remember that y equals 0 is the equation for the x-axis, y equals 0. So the midline is the horizontal line about which the sine curve oscillates. The amplitude is how far above and how far below the midline the graph goes. So the midline is y equals 0, and the maximum point above the line is 1 unit above, and the minimum is 1 unit below. So that's the amplitude. Okay, I'm going to use this graph to show you how to graph the reciprocal of sine. So the graph of y equals cosecant of x, which is 1 over sine of x. So just like in college algebra, if you remember, you had vertical asymptotes for some functions. And so the cosecant of x, y equals cosecant of x, will have vertical asymptotes. And those occur for x values that make the denominator 0. So we use dashed lines for vertical asymptotes. So since sine of 0 is 0, we have a vertical asymptote on the y-axis. For x equals pi, we have another vertical asymptote. At 2 pi, we have a vertical asymptote. And then I'll start on this interval between 0 and pi. The graph of y equals cosecant of x between 0 and pi is going to look like something like this. The graph is going to be asymptotic to those vertical asymptotes, and the reciprocal y equals cosecant of x intersects y equals sine of x at exactly 1 point on that interval. And that makes sense because sine of pi over 2 is 1, and cosecant of pi over 2 is 1 over 1, or 1. On the next interval, from pi to 2 pi, well, the sine values are negative on that interval, and so the reciprocal will also be negative. So y equals cosecant of x on this interval will look something like this. And we have some partial graphs over here, partial periods. So in this interval, the graph would look something like this. If I were to complete one more portion of the sine. Same with this over here if we go to negative pi. So y equals cosecant of x has a vertical asymptote. And so on this interval from negative pi to 0, cosecant of x looks something like this. Okay. Now we'll try to do some more complicated ones. We'll gradually get more and more complicated as we go. So this time we want to graph y equals sine of 2x in the xy plane. And we'll also graph the reciprocal function, y equals cosecant of 2x. Well, the amplitude is 1. The coefficient of sine of 2x is 1. So the absolute value of 1 is 1. So the amplitude is 1. The period is 2 pi divided by 2, or pi. So since we have sine of 2x, we determine the period if we divide 2 pi by the absolute value of the coefficient of x. The absolute value of 2 is 2, so 2 pi divided by 2 is pi. So that's the period. There is no phase shift on this one. You'll see a phase shift in a few minutes. And the midline is y equals 0 again. Okay, I'll show you an alternative way to determine both the period and the phase shift. So this part, this 2x, it's the argument of the sine function. So these values 2x range between 0 and 2 pi. So if we solve this compound inequality for x, we could do so if we divide each of the 3 parts by 2. 0 divided by 2 is 0. 2x divided by 2 is x. 2 pi divided by 2 is pi. So this number on the left is 0. That indicates that there's no phase shift. And the length of the interval is pi. That indicates that the period is pi. So we'll practice this for each of the other ones where we have to. Okay, so we'll get one complete period of this function, y equals sine of 2x, between 0 and pi. So remember what I said earlier about dividing a period into 4 parts. So I'll put pi right here. And negative pi. We'll just focus on 0 to 2 pi to start with. And then we might extend the graph a little bit later. Okay, so if I divide the interval from 0 to 4 into 4 parts, then the length of each of the subintervals is pi over 4. So pi over 4, pi over 2, 3 pi over 4, and pi. The amplitude is 1 and the midline is 0, so the maximum height will be 1 and the minimum will be negative 1. Okay, so let's evaluate y equals sine of 2x for 0, pi over 4, pi over 2, 3 pi over 4, and pi. We'll plot those points, and then we'll have enough information to just go ahead and graph the function. When x is 0, 2 times 0 is 0. Sine of 0 is 0, so the point 0, 0 is a point on the graph. When x is pi over 4, 2 times pi over 4 is pi over 2. Sine of pi over 2 is 1, so the ordered pair pi over 4, 1 is a point on the graph. When x is pi over 2, 2 times pi over 2 is pi, and sine of pi is 0. So we have a point on the x-axis. When x is 3 pi over 4, 2 times 3 pi over 4 is 3 pi over 2. And sine of 3 pi over 2 is negative 1. So we have this point on the graph. And then when x is pi, 2 pi, sine of 2 pi is 0. Okay, so we can sketch in the sinusoid for one period between 0 and 2 pi. If you ever want to, you're allowed to plot more points along the way, but dividing the period into 4 parts and evaluating the function at the endpoints of the subintervals is sufficient to get a graph for that sine function. Okay, if we let's draw 2 more periods. We'll go from pi to 2 pi to the right, and 0 to negative pi on the left. So we'll subdivide each of those. This will be negative pi over 4, negative pi over 2, negative 3 pi over 4. And this one will be 3 pi over 2, 5 pi over 4, 7 pi over 4. Okay, but it's going to follow the same pattern. So here we're going to get an output at 1, output 0, output negative 1, output 0. So here's one more period of that function on the right. And then on the left follows the same pattern on the left. So there you have it. You can verify that you're getting the right outputs just by evaluating the function. So we'll just do one of those. If x is negative pi over 2, 2 times negative pi over 2 is negative pi. Sine of negative pi is the negative of sine of pi, which is 0. So we have a point on the x-axis. Okay, we're going to sketch a graph of the reciprocal function, y equals cosecant of 2x. So wherever sine of x is 0, the reciprocal function, y equals cosecant of 2x, has vertical asymptotes. So I'll sketch in the vertical asymptotes where y equals sine of 2x equals 0. And then we'll sketch the reciprocal function on each of those intervals. So on this interval, since the sine function values are positive, the reciprocal function is also positive. On this interval, negative values. On the next interval, positive values. And so on. I'm sure you get the idea. Okay, so the graph in red is the graph of y equals cosecant of 2x. Okay, next example. Okay, on this one, y equals negative 2 sine of x. Graph that and also graph its reciprocal. Well, the period is 2 pi. 2 pi divided by 1 is 2 pi. There is no phase shift on this one. The amplitude is the absolute value of negative 2, which is 2. And the midline is y equals 0 again. Okay, so we'll sketch one period between 0 and 2 pi. Seems like I ought to be able to draw a straight line, but okay, so we'll divide the interval from 0 to 2 pi into 4 parts, like we did before. So each of those subintervals is of length pi over 2. So let's start plotting points. So y equals 0 is the midline. Okay, so when x is 0, sine of x is 0, negative 2 times 0 is 0. So this is a point on the graph. And then the next input, pi over 2. Sine of pi over 2 is 1. Negative 2 times 1 is negative 2. So the y-coordinate is negative 2. So we'll plot those numbers. So we have this output, negative 2, when the input is pi over 2. When x is pi, sine of pi is 0, negative 2 times 0 is 0, so we have another point on the x-axis. When x is 3 pi over 2, sine of 3 pi over 2 is negative 1. Negative 2 times negative 1 is positive 2, so we're up here. The y-coordinate of that point is positive 2. And then finally, sine of 2 pi is 0, negative 2 times 0 is 0. Okay, so this time we have the sine curve that looks something like this. So remember from algebra, this negative 2 in front of sine of x, that indicates if we take sine of x, we can, the negative 2 sine of x reflects the graph across the x-axis. Okay, let's graph one period of the cosecant, the y equals negative 2 cosecant of x. So that has vertical asymptotes where the sine function is 0. So we have these vertical asymptotes. And I don't have a lot of room, but down here we have this part of y equals -2 times cosecant of x. And then up here, we're off the grid a bit, but y equals -2 cosecant of x is graphed up there. Yeah, this one, graph y equals sine of x minus pi over 2. The coefficient of x is 1. 2 pi divided by 1 is 2 pi, so the period is 2 pi. And this time we do get a phase shift, which is pi over 2. So that's a rightward shift. So I'll just make a note of that in red ink, shift right, pi over 2 units. The amplitude is 1, and the midline is y equals 0 again. Okay, that other technique for finding both the period and the phase shift, we'll do that here again. So these values, x minus pi over 2, those values are between 0 and 2 pi for one period. And then we solve this inequality for x. So all we have to do is add pi over 2 to all three parts. So 0 plus pi over 2 is pi over 2 less than or equal to x. And then 2 pi plus pi over 2 is 5 pi over 2. The length of this interval is 2 pi because 5 pi over 2 minus pi over 2 is 2 pi. And the phase shift is pi over 2. Okay, so we want, in graphing one period of this function, we want to start the period at pi over 2. So this is our left endpoint. And then I'm going to divide the interval from pi over 2 to 5 pi over 2 into 4 equal subintervals. So each of the subintervals will have length pi over 2. So this will be pi, 3 pi over 2, 2 pi, and 5 pi over 2. So the amplitude is 1. I'm going to put it a little higher on this one, a little bit lower down here. Okay, so we're going to start with pi over 2. X equals pi over 2. So in the function, pi over 2 minus pi over 2 is 0. Sine of 0 is 0. So we have this point on the graph. When x is pi, pi minus pi over 2 is pi over 2. Sine of pi over 2 is 1. So for this one, I have the output at 1. When x is 3 pi over 2, 3 pi over 2 minus pi over 2 is just pi. Sine of pi is 0. So the output is 0. When x is 2 pi, 2 pi minus pi over 2 is 3 pi over 2. Sine of 3 pi over 2 is -1. So we have this output at -1. And then finally, when x is 5 pi over 2, 5 pi over 2 minus pi over 2 is 4 pi over 2, or 2 pi. Sine of 2 pi is 0. So we have an output of 0 again. So then we connect the dots, sketch the sinusoid. That's one period of that function. So we'll graph its reciprocal, put in the vertical asymptotes where sine is 0, where it crosses the x-axis. And then in this interval from pi over 2 to 3 pi over 2, the reciprocal function y equals cosecant of x minus pi over 2 is up here. On the interval from 3 pi over 2 to 5 pi over 2, the graph is down here. Okay, let's keep going. Here's the next one. Graph y equals sine of x plus 2 in the xy plane. So the plus 2 is outside or apart from sine of x. So the period is 2 pi. 2 pi divided by 1 is 2 pi. There is no phase shift. The amplitude is 1. And this time, though, we have a vertical shift of 2 units. So the midline is the horizontal line y equals 2. Okay, so we'll just graph one period of this. So let's put 2 pi here. Subdivide one period into 4 subintervals of equal length. So those are the 4 subintervals, each of length pi over 2. The midline is y equals 2. So you probably won't see this done very often, but I'm going to just put a dashed line for the midline. It's not required, but it might help guide us a little bit. So since the midline is y equals 2, and the amplitude is 1, the highest point on the curve will be at 2 plus 1 or 3. The lowest point will be 2 minus 1 or 1. Okay, so just evaluate y equals sine of x plus 2 at those input values. At x equals 0, sine of 0 is 0, 0 plus 2 is 2. So this is a point on the graph. Sine of pi over 2 is 1. 1 plus 2 is 3. So we have this point. Sine of pi is 0. 0 plus 2 is 2. Sine of 3 pi over 2 is negative 1. Negative 1 plus 2 is 1. Sine of 2 pi is 0. 0 plus 2 is 2. So then we just draw the one period of the sinusoid. And then the reciprocal function, the vertical asymptotes. And then, so the reciprocal function is graphed in those 2 places. Okay. Okay, so here's the general form. Y equals a times sine of bx minus c plus d. The period, if it's in this form, is 2 pi divided by the absolute value of b. The amplitude is the absolute value of the coefficient a. The phase shift, if you have bx minus c, the phase shift is c divided by b. And the midline is y equals d. So bx minus c. Remember the alternative for finding the period and the phase shift. I'll just write down the first step. You would write 0 is less than or equal to bx minus c is less than or equal to 2 pi. And then if you solve this compound inequality for x, this number on the left will be the phase shift. The length of the interval will be the period. So we'll do that over here. Graph y equals 3 times sine of 1/2 x plus pi over 4 plus 1. So the amplitude is the absolute value of 3, or 3. Since we have a plus 1 over here, the midline will be y equals 1. The coefficient of x is 1/2. So the period is 2 pi divided by 1/2. But 2 pi divided by 1/2 is 4 pi. And the phase shift is negative pi over 4 divided by 1/2, which is negative pi over 2. So this will be a leftward shift by pi over 2. Okay, but the alternative for finding period and phase shift, we have the sine of 1/2 x plus pi over 4. So if we write 0 is less than or equal to 1/2 x plus pi over 4 is less than or equal to 2 pi, we'll solve this inequality for x. First, we'll subtract pi over 4 from all 3 parts. So we get negative pi over 4 is less than or equal to 1/2 x is less than or equal to 2 pi minus pi over 4 is 7 pi over 4. And then the next step to solve for x, multiply all 3 parts by 2. So negative pi over 4 times 2 is negative pi over 2. 1/2 x times 2 is x. 7 pi over 4 times 2 is 7 pi over 2. Okay, so just as we determined earlier, the phase shift is negative pi over 2. And the length of the interval is 4 pi because 7 pi over 2 minus negative pi over 2. I guess I can write that. 7 pi over 2 minus negative pi over 2 is 7 pi over 2 plus pi over 2, or 8 pi over 2, which is 4 pi. So that's the period. Okay, so let's start graphing. So I have lots of space. I shouldn't mess this up too much. Okay, so we're starting at negative pi over 2. I'll put that right here. Since the period is 4 pi, the length of each subinterval is pi, if I divide that into 4 parts. So if I add pi to negative pi over 2, I'm at pi over 2. And then if I add pi to pi over 2, I'm at 3 pi over 2. And then add pi to 3 pi over 2, I'm up to 5 pi over 2. And then pi plus 5 pi over 2 is 7 pi over 2. The midline is y equals 1. Okay. So it's not required, and it's rarely done, but I'll just sketch in the midline, y equals 1. So now we just evaluate the function, if we can see it, at each of those values that are endpoints of the subintervals. So when x is negative pi over 2, so up here, 1/2 times negative pi over 2 is negative pi over 4. Negative pi over 4 plus pi over 4 is 0. Sine of 0 is 0. 3 times 0 is 0. 0 plus 1 is 1. So we have this point on the graph. When x is negative pi over 2, the output is 1. Okay, then move over to pi over 2. Okay, when x is pi over 2, 1/2 times pi over 2 is pi over 4. Pi over 4 plus pi over 4 is pi over 2. Sine of pi over 2 is 1. 3 times 1 is 3. 3 plus 1 is 4. So we're all the way up here to 4. Okay, the next value, 3 pi over 2 for x. 1/2 times 3 pi over 2 is 3 pi over 4. 3 pi over 4 plus pi over 4 is pi. Sine of pi is 0. So 3 times 0 plus 1 is 1. So we're down here at 1 again. Okay, 5 pi over 2. If x is 5 pi over 2, 1/2 times 5 pi over 2 is 5 pi over 4. And 5 pi over 4 is 6 pi over 4, or 3 pi over 2. Sine of 3 pi over 2 is negative 1. So 3 times negative 1 is negative 3. Negative 3 plus 1 is negative 2. So we're down here at negative 2. You can barely see it. Okay, one more. When x is 7 pi over 2, 1/2 times 7 pi over 2 is 7 pi over 4. 7 pi over 4 plus pi over 4 is 8 pi over 4, or 2 pi. Sine of 2 pi is 0. 3 times 0 plus 1 is 1, so we're back up here. So we get this graph. Okay, so all the sine curves look alike. They just have different amplitudes, different phase shifts, different periods. Okay, now let's talk about cosine. Well, graphing cosine will not be very different from graphing sine. It's just that the y equals cosine of x it's equivalent to the graph of a sine function with a phase shift. Okay, but let's go ahead and fill in these values. Fill in the cosine of x values for the given x values. Cosine of 0 is 1. Cosine of pi over 6 is the square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. Cosine of pi over 3 is 1/2. Cosine of pi over 2 is 0. Cosine of 2 pi over 3, so now we're in the second quadrant. This is negative 1/2. Cosine of 3 pi over 4, that's in the second quadrant, so this is negative square root of 2 over 2. Cosine of 5 pi over 6 is negative square root of 3 over 2. Cosine of pi is negative 1. And then in the third quadrant, cosine is still negative. Cosine of 7 pi over 6 is negative square root of 3 over 2. Cosine of 5 pi over 4 is negative square root of 2 over 2. Square root of 4 pi over 3 is negative 1/2. Cosine of 3 pi over 2 is 0. Cosine, now we're in the fourth quadrant, so cosine is positive. Cosine of 5 pi over 3 is positive 1/2. Cosine of 7 pi over 4 is positive square root of 2 over 2. And the cosine of 11 pi over 6 is the square root of 3 over 2. Cosine of 2 pi is 1. So that's goes through one period of cosine between x equals 0 and x equals 2 pi. Okay, so we're going to start at x equals 0, and we'll stop at 2 pi. So just like we did with the cosine, we want to subdivide this interval into 4 parts. So from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi. Okay, cosine of 0 is 1, so we have this point on the graph, 0, 1. Cosine of pi over 2 is 0. Cosine of pi is negative 1. Cosine of 3 pi over 2 is 0 from up here. Cosine of 2 pi is 1. So we get one period of cosine of x between 0 and 2 pi. So we can point out something here. At negative pi over 2, cosine is 0 again. So notice, if you remember what the sine curve looked like, we can get a graph of cosine of x if we take the graph of sine of x and shift sine of x to the left by pi over 2. We'll see that a little bit more in detail later on. Okay, but the period of this function is 2 pi. The phase shift for cosine, well, there isn't one for this one, even though I mentioned that if we use sine, it would have a phase shift. The amplitude is 1, and the midline is y equals 0. Okay, so just like with the reciprocal function of sine of x, we also can graph the reciprocal function of cosine. So to graph y equals secant of x, we have vertical asymptotes like this, and then the graph of y equals secant of x between negative pi over 2 and pi over 2 looks something like that. Between pi over 2 and 3 pi over 2, it looks something like this. Okay, we can start the last example. We'll fill in this general form information. If we have y equals a times cosine of bx minus c plus d, the period is 2 pi divided by the absolute value of b. The phase shift is c divided by b. The amplitude is the absolute value of a, and the midline is y equals d. So let's see what we can get done. We have a little bit more than 3 minutes left to graph y equals negative 2 times cosine of x minus pi over 2 minus 1. So the period is 2 pi because the coefficient of x is 1. So the period is 2 pi. The phase shift is pi over 2 to the right. The amplitude is the absolute value of negative 2 or 2. And the midline is y equals negative 1. Okay, so let's get started. So the phase shift, pi over 2 to the right. So we're going to start at pi over 2. And then since the period is 2 pi, we'll divide one period into 4 equal parts. So each subinterval will have length pi over 2. So we're starting at pi over 2. And we're going to end at 5 pi over 2. The midline is negative 1. So now let's just start plotting points. Let's see, if you can see those. So we might get this done. So pi over 2 replace x with pi over 2. Pi over 2 minus pi over 2 is 0. Cosine of 0 is 1. Negative 2 times 1 minus 1 is negative 3. So at pi over 2, we have this point down here at negative 3. When x is pi, pi minus pi over 2 is pi over 2. Cosine of pi over 2 is 0. Negative 2 times 0 minus 1 is negative 1. So we're at this point at 3 pi over 2. 3 pi over 2 minus pi over 2 is pi. Cosine of pi is negative 1. Negative 2 times negative 1 is positive 2. 2 minus 1 is 1. So we're up to 1 at this point. And a couple more. 2 pi, when x is 2 pi, 2 pi minus 3 pi over 2 is 3 pi over 2. Cosine of 3 pi over 2 is 0. Negative 2 times 0 minus 1 is negative 1. So we're back down here at negative 1. And finally, when x is 5 pi over 2, 5 pi over 2 minus pi over 2 is 4 pi over 2, or 2 pi. Cosine of 2 pi is 1. Negative 2 times 1 minus 2 is negative 3. Okay, so we graph the sinusoid. The one period looks something like this. Okay, we are out of time for today. Tomorrow we'll look at section 8.2, and then in the second part of the class we'll have the test 1 review. Test 1 will be on Monday during the first 50 minutes. That's all for today.